Good morning, geometry students. I'm very glad that you tuned in today. So if you're here and you're listening, I'm super proud of you because you're doing your part. So I hope that you're having a great day and that your family is well and healthy, and so are you. And so just let's get ready to do this last lesson before Easter break. And I hope that you all, when you get to spend some time thinking about what God did for you and how much He loves you. So make sure that you do spend a good amount of time over the break just chilling and relaxing and getting that good Sabbath rest, we'll call it. And so make sure you get your good rest. But for right now, let's finish up this last new lesson before the Easter break. And then tomorrow will be a review and you'll have a quiz and then you'll have a nice rest. Okay? So today we're going to talk about volumes of prisms and cylinders. We had been talking about surface area, and that would be like the outside part of it. The volume is really what deals with what fits inside of it. Okay? If you can imagine you have a big box and you're throwing in a bunch of cubes, that's what volume is about. That's the easiest way to think about it, and that all those cubes would go in and fit like right up next to each other, so you could actually build something out of cubes. And then you can think about some of the odd shapes where you would build something out of cubes, but then maybe shave off parts of it so that you would have not an entire cube, but part of a cube, and that also would go into counting how much volume there is. Now, some things, especially liquids, it's hard to think about it as being cubes, but just think about it as if it was like a cube-shaped container and you poured a liquid into it, and how many cubes that would come out to be. So these volume units are called cubic units, and a cube that is 1 by 1 by 1 gives you 1 cubic unit. And the volume tells you how many of those cubes it takes in order to fill that solid up completely. Just so that you have a little context, I have some examples of what things are close to the size of various different cubes. Okay, first of all, if we are thinking about a sugar cube, I'll make that a little bigger. Okay, a sugar cube is about 1 cubic centimeter. It's about a centimeter on each side. So if you've ever seen or encountered a sugar cube, that's about 1 cubic centimeter. If you haven't ever encountered a sugar cube, it is slightly smaller than a standard die if you're going to roll dice for a game or whatever it is. So if you're thinking about a cubic centimeter, a standard die is a little bit bigger than that, but it's also a good estimate if you're trying to get an idea of sizes. A cubic foot would be about the size of a medium box. I know that we all are probably getting more deliveries than normal, and it's hard to describe medium, but it's 1 foot by 1 foot by 1 foot. So that would be about a cubic foot. And a cubic meter would be 1 meter tall by 1 meter wide by 1 meter long. It'd be 1 by 1 by 1. So if you think about that doorknob that we talked about in the other lesson as being about a meter high, and think about if you had something that was that high but then also that wide, and then the other dimension also being 1 meter, that would be about how big a cubic meter would be. And if you can imagine in your mind that table in the back of the room, that big brown one, you could probably fit about 2 cubic meters underneath of there if you were thinking about that type of measurement. All right, so just to give you a little bit of a link. So we have some, they're postulates. I'm just going to think of them as like fun facts. They're things that are true always about volume. First of all, volume is always positive because you're measuring a length and a width and a height or some other way of measuring volume. It has to be a positive number. You can't have a negative amount of volume. If you have an actual cube, okay, an actual cube and one of the edges has a length, all you have to know is that one length, and in order to find the whole volume of the cube, all you have to do is take that length times itself times itself. In other words, e to the third power. You hear the word cube in this, we would say this as e cubed, the length of an edge cubed. That's where that term comes from, because it's dealing with the volume of a cube. Also, if you have, just like we had the segments that can be added to make a bigger segment, an angle addition postulate where you can add angles to make a bigger angle, we also have the idea of volume also being able to be added. So if you had two pieces that went together to make one solid, you could find a total volume. So you could think about, let's say you had an ice cream cone that was filled up with ice cream. I always like to do it that way. I don't like to have my cone empty. I like to fill it up. So for me, an ice cream cone is a great example, because all throughout the cone, there's this certain volume of ice cream. So if you knew how much ice cream was in there, and then you knew the amount of ice cream in the blob on the top, then you would be able to add them together, and that would give you the whole volume of ice cream all together. And so that's really what this postulate right here is saying. And then another one that's kind of like should be super simple is that if you had two congruent solids, two that were exactly the same, they would have the exact same volume. And you can think about that as being just anything that you would have identical is identical. So congruent solids have the same volume as well. So let's do some actual examples. There's a lot of examples and calculations on this. So if you have trouble drawing it, remember you're not going to be asked to draw it, okay? So, but if you're taking notes and you want to draw, you can draw a square and then draw a square in the back. And once you have those squares, you're going to connect those sides together. So you can do something like that if you want to draw it, or if you have access to a printer and can print out some of the pages that are blank. You can always do, for the PDF versions, you don't have to print them all. There should be some kind of a setting on your printer where you can put multiple pages on one sheet. And that's how I do that when I make the notes for you guys. So if you choose that setting correctly, then you don't have to use up like one whole page for one silly little picture. You can put several on one page. Okay, so let's say we've got this cube. The one formula that we have so far is that if you know one edge of the cube, then the volume of that cube is going to be that number cubed. So we can just say, okay, well, if I have 4 inches this way and 4 inches this way and 4 inches this way, I can multiply 4 together 3 times and end up with 64 cubic inches. So what that would mean, that it would take 64 1-inch cubes to be able to fit inside of this box. You can kind of picture them in your mind. You'd have 4 this way, but then you'd have another 4 behind it and another 4 behind it, another 4 behind it, and you would have 16 in just one row, but you'd have 4 rows going up. So that's where this idea of volume comes from. Squares and or cubes and rectangles, rectangular solids are good for doing that, to be able to think it through. So for example, here's a formula. It is a theorem that we can think about, but it's really just the fact that the volume is the length times the width times the height. And for what I was thinking about before, think about it here. You've got a whole bunch of cubes that are lined up along the bottom of this, and that would be your length times your width. But then the height tells you how many rows of those that you would need. So how many layers you would need as you were going up. So length times width times height is your formula for that. Yes, I put a capital H on purpose, because that's going to be part of a general formula later on. So just kind of hold on for that for a minute. But for a box, rectangular prism is the special word for a box. For a box, you're doing length times width times height. So let's look at an example here. I have a box 10 centimeters by 6 centimeters by 3 centimeters tall. So I can take my 10 times 6 and then multiply it times 3 in order to get my complete volume. 10 times 6, 60 times 3 gives you 180. And hopefully you're noticing the unit here. Just like for when we were looking for the areas, we had to have square units. For volume, you have to have cubic units. So this is specifically telling you this is how many little cubes it takes. This is how many little sugar cubes or little die that it would take in order to line them all up and to build this box out of them. All right, and it sounds like a lot, and they really do add up fast. In that, it might not seem like they should, but they should. In medicine, interestingly enough, a cubic centimeter is the same as a milliliter. For some reason, when they're going to give liquids in the IV bag, they say something like give them 15 cc's of whatever it is that they're giving. That would be 15 cubic centimeters, which is really another way of saying milliliters. Okay, so that's just a little side something for you to know, because it's good to kind of, when you hear words, know what those words mean. So kind of cool. All right, so another thing that we can think about is you can think about, what if you took that box and you just kind of pushed it sideways a little bit and it's leaning, kind of like the Leaning Tower of Pisa. Okay, so the box kind of went squished a little bit sideways, but when you did that, you have still a length times width, but you've got little cross sections. Okay, think about this. If you had a layer down here, but then there was another layer up here, all those layers would actually be the same size. It would be the same shape as this bottom piece. And the top piece also matches, because remember, a prism has the same top and the same bottom. So it wouldn't matter if this thing got pushed to the side a little bit, you would still have just as many layers. They just would be pushed over to the side. As far as how I can show that is these red rectangles, as long as the length and the width are the same, then the red rectangle here is the same as the red rectangle here if you just squish it over to the side and you've got rectangles going up the top like that. Okay, if you can imagine, if you can think about a slinky, okay, and the slinky's sitting there and you kind of smush it over to the side, so it's still sitting in the base of the slinky, is still sitting in the same place, but it got smushed over to the side kind of like this, so it's kind of slid over. You can think about that same thing with those cross sections as being equal. All right, so what that leads us to is something called capillaries principle, which is that if you have two solids that have the same height, and if all the planes parallel to that bottom part have equal areas, then the volumes are the same. So in other words, when you have that squished over, it's kind of slid over, as long as the height remains the same, which would happen with that slinky if you just slid the pieces over a little bit, that would still stay the same height. So capillaries principle says that the volumes would have to be the same as well. All right, I have not figured out how a way, even if I was standing in front of you, to demonstrate that. I kind of have this strange idea in my head, if I could somehow fill up that slinky with water and then push it sideways over in a tilted pattern like that, you'd see that none of the water would spill out. It would be the same. But I haven't figured out how to do that yet without making a giant mess. Maybe if I lined it with plastic or something like that. So that's just something to think about, that it would still have the same amount of volume inside of it, even if you kind of melted it over to the side a little bit. So what that leads us to is this formula. Okay, the explanations generally lead to a useful formula. Notice that we still have H. I mentioned earlier about the capital H for height. So we still have this H, this capital H for height in both of these formulas. And then we have a capital B, which represents the area of the base. So these two theorems actually 100% are the same theorem, talking about the volume of a prism and the volume of a cylinder. It's just that with a prism, you could have any kind of a shape on the bottom that you want. You could have square or a rectangle or a any kind of a shape on the top and bottom for a prism, as long as they were parallel to each other. But the area of that base, and if you remember when we went over it when we're trying to find surface area, finding the area of the base could involve any one of those formulas, and then times how tall it is. So you can have, for a prism, you'd be looking for one of those areas. When you have a cylinder, we've got this circle on the bottom, and so pi r squared gives you the area of the base times the height. So really same formula, just a matter of how you're finding the base. So I've got some examples for us to go over so that you can see that in action. Okay, here's our summary that I was just talking about. Any cylinder or prism, whether it's right or oblique, volume equals base times height. So we need to work on those. So here, okay, so I've got a prism because the top and bottom are identical polygons. So I want to find the area of the base and multiply it times how tall this thing is. So the area of the base, because it's a triangle, you have to remember your area of a triangle formula is half little b base times height. So we start with 1/2 of 5 times 7. And then multiply that times how tall it is. So first thing you would do would be to multiply the 5 times 7, then take half of it, and then multiply that times 11. And any old calculator will do that for you, or even do it by hand if you want to. So we have 192.5 cubic centimeters. So what that means is you'd be able to build this out of 192.5 little cubic centimeters. You'd have to cut some to get these little pointy parts in here, but you would be able to take 192 of them and build them. If in the case of a candle, candles are great. If you've ever gotten a chance to make candles, because you melt down the wax and you pour it in. So if you had a certain volume, and you've counted out how many chunks of wax you need 192.5 chunks of wax. You could melt it down, pour it in the mold, and it would fill it all in and make that volume. So it's good. Now, candle making is a little bit more complicated than that, but you get the idea as far as how that would go. You could smush it down. Play-Doh is another good example. If you had little dice-shaped pieces of Play-Doh, you'd need 192.5 of those little guys to smush down and change their shape to make into that. Okay? Let's look at another one. This one happens to be oblique, which means it's not standing straight up and tall. But we do have a base, and we do have some information about it. This little arrow here is pointing to the apothem, and then this is the length of one of the sides. Remember, we had an area of a regular polygon formula. If you know the apothem and one of the sides, notice that this is a pentagon, and then the height of the prism is kind of over here to the side, just telling you from the bottom to the top how tall it is. So we are looking for base times height again. Our base, though, is that formula, 1/2 of the perimeter times the apothem times the perimeter. Sorry, 1/2 the apothem times the perimeter. The apothem here is 1. And the perimeter is 5 times 1.4. 1/2 apothem times perimeter. So we have our base area here and then our height as 3.8. So you do need to do some calculations here. These numbers are all multiplied together. Okay, so even if you're using a simple calculator, what you can do, oops, I did not want to get the huge calculator. There we go. What we can do is we can, take our numbers and we're going to just put them in here. 0.5 works for 1/2 times 1 times 5 times 1.4 times 3.8. And your phone calculator, any calculators have the same functionality, so you can just plunk that right in there. So you have 13.3 cubic centimeters. Okay, good. Here we have a volume. We want the volume of this. So once again, volume is base, big B base, meaning the area of the base, times the height. Remember, area for a circle is pi r squared. We have our r, this is inches, 4 inches, 8 inches. Pi r squared, pi times 4 squared, times the height, times 8. Once again, you can do this with any calculator that you have. Now the fancy ones are nice, and I do need you to make sure you have one for Algebra 2, because there are some things in Algebra 2 when you get to that you can't do with these. Okay, but for right now we're making do with what I'm sure that you all have. Okay, so you can do 3.14, or you can do pi 3.14 times 16 times 8. Now this one is the most basic of basics. Notice there I have 402.1, but that's because I used a little bit more accurate than 3.14 in mine. Most of your calculators, if you turn your phone calculator on its side, you'll get the scientific one. So here, I believe there is actually a pi here, so I could do pi. Look at all those digits for pi. So this is going to be a lot more accurate, times 16 times 8. And there's my 402.1 that I get when I use the whole pi rather than just 3.14. So it does throw you off just a little bit by estimating with the 3.14, but it gives you close. Okay. I would prefer you use the scientific one and use all the digits for pi. So scientific on your phone, if you turn it sideways, some of them are turned sideways, but you'll find it easily enough. Or the real TI-83 Plus, which is the better calculator for you that you'll need for Algebra 2, or something basic if that's all you have. Okay, so 1/2 base times height. Here's a circle again. Remember, pi r squared for the area of a circle. And then times the height, which is 10. So 25 pi times 10. 250 pi if you did it in terms of pi, or 785.4. So we can do 250 pi. Clear that out. 250 pi. Oops, and have to do times 250. So 785.4 about cubic centimeters. Now they are approximate values, but the amount away from the actual value is so minimal that we can do rounding, and for real life purposes you would need to do just a little bit of rounding for that. Okay, so that's it. You are now, you need to make sure that you do a good job with assignment 54. And tomorrow we're going to be doing a review for your quiz, going back over things. You'll receive by email your quiz on Thursday. I do not want anybody staying up late on Wednesday, please. Okay, please make sure that you've done all of your schoolwork early so that you can rest on Wednesday night. Get involved with some kind of obviously not a face-to-face get-together, but the source or some place where you can fellowship with people and get closer to God and pray and do all the things that you need to. So I'm leaving that open for you. I'm specifically shutting down links and whatnot on Wednesday night so that people are not trying to do their work when they need to be freed up. And then also then on Thursday, I'll open the quiz up early for you so that you can get to it, do it, get it done, and then have your 6 school days off after that. So that'll be great. All right. And so have a really great day, everybody. And I am praying to see you sooner than later for a whole lot of reasons. And I'll pray for your families too, for safety and protection. And I'll see you soon, I hope.